Okay, thank you. All right, so we have, the videos have converted for the first half. It'll be July 27 A1 and July 27 A2. So it's kind of broken up because of that break in our internet. But the second half of it will just be July 27 B. So look for those 3 different videos for today's session if you want to review. Okay, so we talked about how to form an enol and the fact that even though we don't have very much of it there, we can use that reactivity of the species formed to give us our new products, okay? So the first reaction I want to do is not necessarily creating a new carbon bond, but we're going to create a new carbon halogen bond. And we're going to use that carbonyl to direct it. And it has everything to do with the idea that the enol form is the part that's going to react with our incoming halide, and that will generate our substitution at that alpha carbon. Okay, so in the case of the acid catalyzed hydrogenation, in the acid catalyzed halogenation of a carbonyl compound, we end up thinking about, okay, acid catalyzed, we're going to protonate our ketone to give us our enol form right here. And then we're going to have some reaction with that alkene with bromine to give us our final products. And if it's acid catalyzed, that means we're going to somehow generate our acid at the end. Okay, so let's look at that stepwise here, and let's try the black ink right now. All right, so what we can do is we can take any ketone or ketone-like substituent, as long as it has at least one alpha hydrogen. We can take a drop of acid catalyst and a halogen, and we can halogenate at that alpha carbon position and generate a little bit, one equivalent of HX. Okay, unlike the addition of bromine across a double bond where you end up with 2 halogens on here, the fact that it still stays bonded to the oxygen means we only get 1 halogen, and we get 1 equivalent of the acid from it. Okay, so as we would suspect an acid catalyzed reaction, the first step is to protonate our carbonyl species. Okay, so we start with our tautomerization between the ketone and the enol form to give us our alkene. Once we have our alkene formed, our alkene is the electron-rich species and reaches out and grabs at one of the bromines, generating a new carbon-bromine bond. Okay, when it does that, the electrons can kick in from the oxygen here to give us regenerate our protonated ketone species. And then our water comes in and regenerates our acid, and we end up with our final product here. Let me move it over here, right here, which is our alpha bromo ketone now. So our bromine is now that 1 carbon off of the carbonyl. Okay, so once we've done one of these in an acid catalyzed system, the reaction stops. Okay, so with what the product we'll get here is the monobrominated ketone species. Notice that I say up here, it's racemic, okay? Meaning that if you started with a chiral center here and you did this reaction with your acid here, you're gonna end up with a mixture of R and S substitution, okay? And remember why we end up with that mixture of R and S substitution is because we went through that hybridization change. We went from an sp3 hybridized carbon to an sp2 hybridized carbon. And remember when we did all those reactions with alkenes or sp2 hybridized carbons, we could not control stereochemistry because you could get a top attack from the top or bottom of that trigonal planar structure. And so we always get racemization when we go through that intermediate. Okay, so we always get a mixture of R and S from these substitution products. Okay, so once we've done this, it stops at a single halogenation, either bromine, chlorine, etc. It'll stop, okay? However, if we change the mediation from acid to base, we can actually get multiple substitutions at that alpha carbon if you have multiple alpha hydrogens, Okay. All right. So in the case of the base promoted halogenation, oh, come on. Sorry about that. All right. That's the acid catalyzed one. In the case of the base promoted halogenation, right here, we can actually replace all of the alpha hydrogens. So if you have one alpha hydrogen, it's going to do one time. If you have two alpha hydrogens, it'll do dibromination. If you have three alpha hydrogens, it'll actually convert it to the tribromomethyl group. Okay. So, and part of the reason that is because as long as there's an alpha hydrogen, I'm not going to do it again. As long as there's an alpha hydrogen for the base to pull off, you're going to keep generating that anion, and that anion can then keep forming a double bond, which can keep reacting. Okay, so let's blow up the mechanism down here below. Okay, so in the base mediated system, the first thing is to pull a proton off of that alpha carbon. Okay, so when you do that, you create your anion here on your carbon, which of course is then resonance stabilized back and forth between the enol keto. So we formed our enolate because it's an anion, and we've shared that negative charge over the carbon and the oxygen. Okay. So what can happen after that is then our anion, so we can either have our double bond now do the same thing it did in the previous mechanism, reach out and grab our bromine and generate our new carbon-bromine bond, and then our electrons will kick in and form our carbonyl compound. Okay. So if there is no alpha hydrogen, then the base reaction stops. Okay. If you have an alpha hydrogen, we've generated another equivalent of base, and therefore we can use another equivalent of base to deprotonate this, giving us our enol intermediate again, which can then react with another equivalent of bromine, which can give additional substitutions. Okay. So in the case of having this halogenation reaction in base mediated, because every electron and drawing group you add to that alpha carbon increases the acidity of that hydrogen because it's pulling electron density away from it, making it more acidic, it actually speeds the reaction up. And so you replace all of the alpha hydrogens. Again, if you have three alpha hydrogens, it's going to take it all the way down to a trihalo compound. When we do that, that has a special name for it. We call that the halo form reaction. Okay. So typically in the halo form reaction, we're talking about reactions where we have a methyl ketone. Okay. So when you have a methyl ketone, that means you have three alpha hydrogens. Okay. And so all three alpha hydrogens can react. Now, once we do that, we now have a trihalo methyl group. The trihalo methyl group is actually a really good leaving group because it can stabilize the negative charge. It's the best leaving group of a carbon anion possible. And so what we see is we get the substitution of all three alpha hydrogens to generate a trihalo carbon species. And now it's such a good leaving group that if you attack the carbonyl with a nucleophile, it's going to displace this trihalo carbon compound and generate a carboxylic acid. Okay. Okay, so the keys for haloform reaction is it must be base catalyzed, because if it was acid catalyzed, it'd stop at one halogenation. Okay, so it has to be base, and it has to be a methyl ketone. It has to be a methyl ketone because you have to have three alpha hydrogens to substitute to give us that trihalo carbon as our leaving group. And then just like any other nucleophile coming in here, once we get to our tetrahedral intermediate space, we need to find the best leaving group. And the best leaving group is usually the weakest base. And in this case, when we protonate our species here, we get this much weaker acid and our much weaker base from our products. Okay. Okay, Carrie has a question.
Yeah, so the products for this one, like is there like a major and a minor, or are they both?
They
Is
are
it?
equal. You get the benzoic acid salt because you're still in basic conditions until you acidify, and you either get the trichloromethyl or the tribromomethyl or the triiodomethyl. They are in equal portions. It's 1-to-1.
Okay, thank you.
Because the carbon you're taking off is this one right here. So you get, for every equivalent of benzoic acid you get, you're going to get one of the halo form, the chloroform, bromoform, or iodoform.
And where did the hydronium come from?
That was the base we added to the reaction to drive it. Notice we're using 3 equivalents of base here.
Yeah.
So
Okay.
you need at least 3 equivalents of base. That's just to generate this tribromo species or trihalo species. And then we need another equivalent of base to displace the CX3.
Okay, thank you.
Okay, so we use a lot of hydroxide in this reaction. Very good question. All right, no other hands raised? Okay. All right. So there's a derivative of this reaction where we try to just pull off one of our alpha carbons and replace it with a halo compound, okay? And this is called the HVZ reaction, or Hell-Volhard-Zelensky, okay? Now, the reason these are kind of cool is because you're giving yourself something that can be displaced by a nucleophile next to a carboxylic acid. Okay, it's not on the carboxylic acid carbon like we did last chapter, where we're doing substitutions with that. We're actually doing substitutions on the carbon next to it. So you always generate a carboxylic acid plus some kind of halogen you can do additional chemistry on. Okay. So the reagents in this particular one are, you use the halogen right here, and then you use phosphorus right here. That's phosphorus elemental, not any kind of complex. And so the first thing that's going to happen is we're going to be generating our acid halide in situ, okay? Remember, we generated acid halides in the last chapter, and we typically used a phosphorus compound like phosphorus trichloride or thionyl chloride. In this case, the phosphorus and bromine react together to give you an intermediate that is the phosphorus tribromide, okay? Once we form that acyl bromide, that's actually our reactive species, and we can use that to form our tautomer, which will give us our enol form here, which is protonated by the acid generated by removal of this hydrogen here to give us our brominated species. Notice we have a halide on here, okay? So that will stay there until the second part of the reaction when you add water. So we add water to the reaction here. That's going to hydrolyze off the acid halide right here, generating HBr, and you end up with your final product right here. So you have an alpha halo carboxylic acid. Okay, so, and this again, it stops at a single halogenation because it is acid mediated. Okay, so what can you do with this once you form it? Well, you can make a wide variety of other things. And actually, I'm going to show you how to do it with a different reagent. Okay, sorry. So another way to do it, instead of using bromine by itself, we can actually use what we call NBS, or this is N-halosuccinimide, okay? And in this case, we've already pre-complexed our halogen with this nitrogen anion to give us our halo, like in this case, bromine, as a positive charge right here. And so now we have our bromine is going to be attacked by our nucleophile, okay? So in the case of the species here, we can actually get selective halogenation. We can put whatever halogen we have on this NBS, and it stays exactly in this alpha position. So in the case of this right here, we could add bromine and still have our acid halide. In the case of if we used iodine, we can actually put an iodine there and still have our acid halide. Get very specific substitution at that alpha carbon. So we can add a chlorine there with phosphorus and chlorine. We can add a bromine there with bromine and phosphorus, or we can add an iodine there with just using elemental iodine and thionyl chloride to make sure this stays as the acid chloride. We want to make sure it stays as the acid chloride. Okay, so now what can we do with it? Okay, we're going on. Okay, now that we have that halogen at that alpha position, it can be attacked by other nucleophiles to displace it to create new carbon-carbon bonds or new other bonds with the nucleophile here. So because it's an alkyl halide, our alkyl halides are very susceptible to SN1 and SN2 type reactions, nucleophilic substitution reactions. And so by having this directed to that alpha hydrogen, you can displace that to give you your alpha halogen, and you know your reaction is going to happen exactly at that spot right next to your carbonyl. Okay, and we can use that to our advantage to generate longer and longer and more complex chemical compounds. Okay. So, and this can also be done with just creating the enolate. Using a base to pull that proton off will generate your enolate, which will then still allow you to attack it. I'm sorry. If you do it the opposite direction, you now form the nucleophile. This, your enolate is the nucleophile, and you could attack things that are electrophiles to generate other compounds from it. So you use the halo reaction here to use it as the substrate for attack by nucleophiles, or you can deprotonate it and it is the nucleophile and it can attack other species. All right, so here's a couple reactions on what we can do once we have that halo acid, that alpha halo acid. It can, again, be chlorine, bromine, or an iodine are the most commonly used. So once you have your halogen that is in that alpha position here, if you attack with hydroxide and then protonate at the end of the reaction, you can end up with an alpha hydroxy acid. Notice we made alpha hydroxy acids last chapter as well. This is a different route to form alpha hydroxy acid. Now, we can displace it with any nucleophile. So instead of using hydroxide here, if we use two equivalents of an amine, the nitrogens, the lone pair on the amine acts as the nucleophile, and we can actually generate amino acids, okay? And of course, amino acids are used a lot in biological systems. And so we'll see that in a lot of ways to make these amino acids, alpha amino acids, because it's on that alpha carbon. All right, questions on this substitution so far? So if we want to put one halogen on there, we do it with acid catalyzed system. If we actually want to oxidize that methyl group off completely, we use base catalyzed haloform reaction. Once we have one of those halogens on that alpha position, it can be displaced by any number of nucleophiles. All right, so now let's look at electrophilic reactions with these alpha halocarbons, okay? So the first one we can think of is if we have a halogen and we treat it with base, we have the opportunity for going on E1 or E2 elimination, okay? Now, when we had the elimination, we would have to look for the more stable leaving group such that you would see you could get the more substituted alkene versus the less substituted alkene. In the case of the alpha halocarbonyl compounds, you always form the double bond in conjugation with the carbonyl group, okay? So this makes it a nice way to put it exactly where you want it, is to, you get your bromination at that alpha position using your acid catalyzed alpha halocarbonyl carbonylation right here. And then by treating it with a very big bulky base to force it to be E2. Remember, E2 is when you have a big bulky base and it has to pull a hydrogen away, one carbon away from your bromine, okay? There are no hydrogens on this carbon here, so it has to pull the hydrogen off of this carbon, generating your conjugated double bond with your carbonyl compound. So it's your unsaturated carbonyl compound, okay? And it'll always be conjugated because you knew exactly where the bromine started. Okay, another way to do this is to, instead of halogenating the system, you actually turn the carbonyl compound into the nucleophile by using a base. So in this case, we're going to use a strong base, LDA, and it's going to remove one of the alpha hydrogens. Notice this is symmetrical, so we don't have to worry about which is the thermodynamic and which is the kinetic product. Once we form that anion, the anion is the attacking species right here. This can then be used to displace any other alkyl halide in an SN2 reaction. So we're now generating another way to create a carbon-carbon bond and do it specifically in that position next to a carbonyl compound, because we know when we deprotonate it, it's going to be alpha to the carbonyl compound. Our little smiley nucleophile can then displace an alkyl halide to generate our new carbon-carbon bond. Okay, so we can use these reactions to create a new carbon-oxygen bond in our alpha hydroxy acids. We can do it with a nitrogen where we can create our alpha amino acids. And now we can also do it with extending our carbon chains, but we're using our enolate anion as our nucleophile to displace halogens. Questions on that? Carrie, do you still have your hand up?
No, I'm sorry. Let me change that for lower hand.
Okay, there we go.
Sorry.
Oh, no problem. Okay. All right. Yeah. So in the rest of this chapter and in the next chapter, we're going to talk about these reactions with these anions we're forming on carbon and the different kind of substitutions we can get on them. Okay. So we're looking at nucleophilic reactions of carbonyl compounds at that carbon alpha to our carboxylic acid, our ketones, our esters, or our nitriles. Okay. So in this case here, we're looking at something that has, let's look at this ester right here. And notice there's only alpha hydrogens on this one carbon here. Okay. So this makes it really nice in the fact that we know exactly which side of the molecule we're going to deprotonate. And when we use one equivalent of LDA, we're going to deprotonate just at that alpha position. And that is our nucleophile for other reactions. So in this case here, we're actually attacking the ethyl iodine here. And once we work up the reaction, we have this mono-substituted reaction because we used one equivalent of LDA to create one enolate. That one enolate then acts as the nucleophile and creates one substitution, one additional substitution at that alpha carbon. Okay, and we can use that with any group that can form that alpha, that acidic alpha hydrogen. So it can be a cyano group, it can be an ester, a ketone, or a nitrile. Aldehydes do kind of work, but we're going to talk about that in the next chapter. They actually do, but they do side reactions. And so we'll talk about those side reactions in the next chapter. Now there's a whole series of these reactions where we create these enolates and we can react them with similar substrates or themselves. And we'll talk about those in chapter 19. But we're going to use this recurring theme of generating an anion alpha to a carbonyl or carbonyl-like substance to use it as a nucleophile for the next two chapters. Okay, so We saw at the beginning of the talk that the more carbonyl compounds you have alpha to those hydrogens, the more acidic it gets. Okay, so now I want to start talking about the enolates we create from having two carbonyls that are spaced 1 carbon apart. Okay, and we call those beta dicarbonyl compounds. So we have a carbonyl compound, a carbon with alpha hydrogens on it, and then a second carbonyl compound. So these can be esters, these can be nitriles, these can be ketones, okay? But the key here is we have a carbon in between the two that has an alpha hydrogen, okay? Because of the fact that we have these two electron withdrawing groups, both pulling electron density away from that, that makes those alpha hydrogens particularly acidic, okay? It drops the acidity down so that it can be removed by very, very weak bases, including hydroxides, to form these compounds. Now, once we deprotonate these right here, just with these weaker bases like hydroxide or alkoxide right here, we have a benefit in the fact that we have an additional resonance contributor, okay? In our first species, we only formed the enol on one side and had the negative charge shared on the oxygen. And so it would resonate back and forth between these two species here, okay? When you have the second carbonyl compound in conjugation, you have the opportunity to have a third resonance contributor. That anion can be on that other side, so that now we can have our negative charge spread out over a total of 3 atoms. And so these are particularly acidic, and they are particularly good as nucleophiles. Okay, so notice now the attacking species is our negative charge on carbon here. And this is what's going to do the work of creating our new bonds to carbon. Okay, have just a few minutes left, so let's go ahead and rally forward and look at how we can use this to our advantage. So we learned in the last chapter that if we had a carbonyl compound in conjugation with carboxylic acid, that we could do a thermal decomposition. Okay, and remember that mechanism involved forming that 6-membered ring where we can transfer the hydrogen from the carboxylic acid to the ketone, okay, and then we could remove CO2 from the system, okay. We can use these carbonyl carboxylic acid compounds to generate really complex, very interesting systems, okay. So let's review. The first step here is the actual removal of the CO2. Again, we did the mechanism in the last chapter. The mechanism involves this 6-membered ring where we just rearrange it so the hydrogen can be transferred to the carbonyl from the carboxylic acid. And then it again generates, after the CO2 leaves, our enol form. Okay. And unless that's the most stable form, it obviously tautomerizes to its keto form. And so we can generate our ketones and our decarbonylated products because of that intermediate. So now that we know we can do that decarbonylation, let's build on these alpha hydrogen center here that is in between those two carbonyl compounds. Okay, and we typically do something like where we have a dicarbonyl compound. The first one I want to talk about is what we call malonic ester. Okay, now remember in our dicarboxylic acids, we had oxalic, malonic. If we make the diester of that malonic ester, of that malonic acid, we end up with a single set of alpha hydrogens. And those single set of alpha hydrogens are right in between two carboxylic acids, and it's particularly easy to make our enolate ions from these alpha hydrogens, okay? Now, if you use one equivalent of base, you can create that anion and displace it and substitute that one alpha hydrogen, and then through heat and acid, you can remove one of the carboxylic acids. And so what you end up doing is you end up adding a CH2 and a carboxylic acid to the end of an alkyl chain. Okay, so you can take any alkyl halide. Let's say you had a C10 alkyl halide, and with this malonic ester synthesis, you will generate an additional carbon plus an additional carboxylic acid. Okay, so it's a great way to add a total of 2 carbons to an aliphatic alkyl halide. Okay, so the first thing we do is we deprotonate one of these alpha hydrogens to generate our enolate, use our enolate as our nucleophile to do a substitution reaction on our alkyl substrate. And then by thermal decomposition, we can decarbonylate, yielding our carboxylic acid at the end. Note that when you do this acidification and decarbonylation, the first step is actually clipping off the esters and turning it into the carboxylic acid. The second step is actually the decarbonylation, but they both happen in that same reaction step. Okay. All right, so let's look at that mechanism in a little more detail, and that might be where we get to today, but let's go ahead and try. So again, if we look at either side of those carbonyls, we only have one set of alpha hydrogens. There are no alpha hydrogens here and no alpha hydrogens here, which means we must deprotonate here. Plus, it's got 2 carbonyls, so it's going to be very much more acidic. So the first thing we're going to do is we're going to form this anion right here. And even though it has those 2 other resonance stabilized systems, the carbanion here is our primary nucleophile, that when it comes in, it can displace an alkyl halide through an SN2 reaction to generate our first species right here. And this is our substituted malonic ester. Okay. One equivalent of base creates one enolate. That one enolate is the nucleophile and displaces one halide to generate our monosubstitute system. Once you have that ester, you clip off that with your acid and your water. And by heating, you can form that 6-membered intermediate and decarbonylate, remove one equivalent of CO2, and have the other part of your malonic ester be attached to your alkyl chain. Okay. And let me just show you these malonic acid ester examples, and then I'll move on to something else tomorrow. Okay, so now once you do a single substitution on that malonic ester, you can actually then clip off your chain and have your carboxylic acid. However, you don't have to stop there. Okay, so let's look at the first step here. We can take our malonic ester here, and we have 1, 2, 3, 4 carbons in this butane, this butyl butane right here. And so we're going to end up adding 2 carbons to the carboxylic acid. We're going from butane to the hexanoic acid because we add the CH2 plus the carbonyl carbon. First step is deprotonate, create our anion. Our anion comes in and displaces bromine to give us our intermediate. And then through our acid catalyzed decarbonylation, we end up with our monoacid in pretty good yield, 75%. Okay, but let's say you didn't want a straight chain acid, you want an actual branched carboxylic acid there. Well, we can do that because once you do a single deprotonation here and you get your alkyl group here, you still have an alpha hydrogen. Okay, so what you can do is you can then use a base. In this case, we're using a stronger base, so that we, a T-butoxide in this case. It's going to deprotonate that, again, generate your anion. Your anion is going to act as your nucleophile, and then you can put in a different alkyl halide. You can do this stepwise. You can have 2 different groups attached to your system, okay? Then when you go through your hydrolysis step, you'll generate your diacid. And then, of course, if you do your thermal rearrangement, kick out CO2, you'll now have your di-substituted carboxylic acid. And then they're di-substituted in the alpha position. Okay, and this can be, again, symmetrical or unsymmetrical, You can even do it as a ring. If you had a dihalide compound, you can actually pull it up in a nice little bow. Okay, and we'll talk about that again later. All right, we're right at 1:40. We had a little technical issue, but we'll continue on tomorrow with some additional reactions with these dicarbonyl compounds. Okay. All right, I'm going to stop recording and you can ask questions.